Thank you for introducing me. I'm Hayato Nishimura from Tohoku University, Japan. Today I'm talking about the hydrogen diffusion behavior in a stretch-formed high-strength steel sheet. Recently, high-strength steels applied for automobiles to improve impact safety and reduce car weight. This is an example of the practical application of the high-strength steel sheets for automobiles. As you can see, some of the frame parts are made of the ultra-high-strength steels with tensile strength of higher than 980 megapascals. However, it is reported that with increasing the strength of steels, the risk of the hydrogen embrittlement increases. So, hydrogen embrittlement becomes a critical issue for high-strength steels to use. Automobile steel sheets are mainly used for body frames, and they are mainly used after press forming, such as written in these schematics, stretch forms in here. After that, residual stress and plastic strain are introduced into the steels, so they may change the hydrogen diffusion behavior, resulting in the high change of hydrogen embrittlement properties. So in order to apply the high-strength steel safety, observing the hydrogen diffusion behavior in the steel is needed. There are many kinds of methods to observe hydrogen diffusion behavior in the materials, but most of them are produced by using expensive equipment such as electronic microscope. So they have high spatial resolution, but the observation area is limited up to several square centimeters. So it is difficult to apply these techniques for big specimens such as stretch-formed specimen. In order to overcome this problem, we developed a new method by using iridium complex. The color of this iridium complex changed from yellow to orange by the reaction with hydrogen. So we can observe the hydrogen by the color of the iridium complex with digital camera. So we can observe in wide observation area and in situ. If we can apply this technique for stretch-formed specimen, we can investigate the effect of stress and strain on the hydrogen diffusion behavior. So the objective of our study is summarized here. We tried applying the hydrogen visualization technique by using iridium complex for stretch-formed specimen, and combined with stress and strain distribution obtained by finite elemental methods, we investigate the effect of stress and strain and stress on the hydrogen diffusion behavior of the stretch-formed steel. There are experimental procedures. We use tempered martensite steel rods with 60 millimeters of diameter, and the chemical composition of the material is shown in this table. And the rod was annealed at 850 degrees for 2 hours and quenched into the oil and tempered at 530 degrees for 3 hours. And the rod was sliced in 1 millimeter and polished mechanically and electrically. After that, the sheet was stretch formed and 4.2 millimeters of the stroke displacement by using universal testing machine. One side of the specimen was used as a hydrogen detection site. Only the surface of the hydrogen detection site was plated with palladium and formed the iridium complex film by spraying the mixture of the acrylic paint and methanol solution containing 40 grams per liter iridium complex. This specimen was fixed to these cells, and the cell was filled with 3 weight % sodium chloride aqueous solution containing 3 gram per liter ammonium thiocyanate. And hydrogen was charged by cathodic method, cathodic charging method, and potential was set as minus 1.3 volts versus silver chloride electrode, and hydrogen was charged for 20 hours. And the color of iridium complex was observed by digital camera during the hydrogen charging every 5 minutes. The hydrogen diffusion behavior was analyzed by Python, and we obtained the RGB color value from the pictures and converted them to HSV color space. We represented brightness value, and we focus on this V because the color of iridium complex change becomes dark by the reaction with hydrogen permeates through the specimen. The changing ratio of V with time was approximated by this sigmoid function. Red dot means indicated the brightness value ratio, and blue line is a fitting curve. Hydrogen breakthrough time was defined as an intersection of the tangent line at inflection point and initial brightness value ratio. FEM was processed by Abacus CAE by using 2D axial models and to obtain the distribution of stress and strain. We actually use this model, and this is a stress and strain curve of the materials obtained by tensile test. There are the results of hydrogen visualization test. This is the color changing behavior of the iridium complex. Thank you. As you can see, the color of the iridium become dark. Actually, this is a time-lapse movie of the iridium complex for during hydrogen charging for 10 hours. And there are the pictures of iridium complex during hydrogen charging for 0 hour, 3 hours, 6 hours, and 20 hours respectively. As shown in the previous slide, the iridium complex becomes dark, and we can say that iridium complex successfully reacted with hydrogen permeated through the specimen. In order to figure out the hydrogen diffusion behavior in details, these pictures were numerically analyzed by focusing on brightness. This is the result of the changes in the time, in the V ratio with time, as the point from A to D indicated in this picture. The changes in the V ratio depended on the points. The V ratio changes slowly at point A and fast at point C and D. Using that data, we calculate the distribution of hydrogen breakthrough time every 300 micrometers along this arrow. This is a relationship between the hydrogen breakthrough time and the distance from the center of the specimen. The hydrogen breakthrough time was long around the center of the specimen and became shorter, and then it became constant. So you can see the hydrogen breakthrough time was clearly changed due to the deformation. And we can say that hydrogen visualization technique by using iridium complex is able to apply for straightforward specimen. There are the results of FEM. Upper figure shows the distribution of hydrostatic stress, and lower figure shows the distribution of plastic strain. Hydrostatic stress and plastic strain were complicatedly introduced into the specimen. So I will compare them with hydrogen breakthrough time, respectively, from next slide. This is the relationship between the hydrogen breakthrough time and the hydrostatic stress. It is reported that hydrostatic stress gradient is the driving force for hydrogen diffusion. For example, hydrogen diffusion will be accelerated in this area and retarded in this area. However, the hydrogen breakthrough time was long around the center. So we can say that hydrostatic stress has small effect on the hydrogen breakthrough time. And this slide shows the relationship between the hydrogen breakthrough time and the plastic strain. The distribution of the plastic strain and the distribution of the hydrogen breakthrough time corresponded. Plastic strain increases dislocations. Originally reported dislocations works as a hydrogen trapping site, so it is considered that plastic strain retards hydrogen diffusion. This results assist this fact. So we can conclude that plastic strain has big effect on the hydrogen diffusion, hydrogen breakthrough time. I would like to conclude today's talk here. The hydrogen visualization technique by using iridium complex was available for the uneven surface specimen, such as stretch form specimen. The hydrogen breakthrough time was the longest around the center of the specimen and decreased according to the distance from the top. Finally, the hydrogen breakthrough time changed due to the plastic strain, although the hydrostatic stress has small effect on it. So we can conclude that the plastic strain has affected on the hydrogen breakthrough time of a stretch form specimen. That's all of my presentation. Thank you for your attention.